Hello, everybody. Welcome to a new episode of our machine learning security seminars. Today we have Antonio Orvieto from the ELLIS Institute Tübingen and MPI with a talk on improving capabilities of efficient foundation models beyond language. For your information, this presentation will be recorded, so we kindly ask you to accept the privacy policy when joining the seminar. We will upload the recording to our YouTube channel, where you can find all the information about the seminars and all the recording from past events. If you are interested in learning more about this topic, on the same YouTube channel, you will find a short course on machine learning security. Okay, now before we start, I want to thank all the other co-organizers of this seminar series. Among them, Maura, who will introduce today's speaker.
Thank you, Raffaele. I'm very happy to introduce today Antonio Orvieto. Antonio studied control engineering in Italy and Switzerland, and he holds a PhD in computer science from ETH Zurich and spent time at Google Deepmind, Meta, MILA, INRIA, HILTI, a lot of places, different countries as well. He is currently Hector Endowed Fellow at and Principal Investigator at the ELLIS Institute in Tübingen, Germany, and independent group leader of the MPI of Intelligent Systems, where he leads the Deep Model and Optimization Group. He received the ETH Medal for Outstanding Doctoral Thesis and the Schmidt Sciences AI 2050 Early Career Fellowship. In his research, Antonio strives to improve the efficiency of deep learning technologies by pioneering new architectures and training techniques grounded in theoretical knowledge. His work encompasses two main areas: understanding the intricacies of large-scale optimization dynamics and designing innovative architectures and powerful optimizers capable of handling complex data. And now, Antonio, the stage is yours.
Thank you. It's such a warm introduction. I don't deserve so much. I'm glad to be here. I'll just share my screen before further ado, right? Just so that you see something when I talk. Okay. So thanks, Mara, for the introduction. I'm very happy to talk to like sort of maybe a different audience. So maybe given the title of the seminar, it's for me also very interesting to know more about what you do, and but maybe can bring something like a different perspective maybe on some aspects about intelligence which are maybe not related to security but are related to capabilities in some way. What I'm interested in is to improve what models can do, so maybe you can make it safer too. And so I think there is a interplay between the two areas, and more in the future, of course. So my talk is about improving capabilities of new foundation models beyond language. The beyond language is given by, in some way, like it's going to be just one or two slides that really beyond language. But let's get started. So maybe just to give you a little bit more of my perspective or where I come from. My group is called Deep Models and Optimization. So there's two aspects of it, and in some way I care about both. So first of all, like my background also as well, I come from convex optimization and control. So that's in some way like way I started going through AI was that area. So I'm in general very interested in understanding the optimization properties of large-scale systems, how to derive new algorithms, and to study convergence of algorithms in large-scale non-convex problems, such as training deep learning models. So I'm interested in fundamental aspects and in aspects about scaling. But on the other hand, scaling alone sometimes is not sufficient, or just being faster in optimizing sometimes is not sufficient. So what I'm mostly interested in is derive powerful models that can also go beyond pure language models and chatbots in a sense, or maybe coding in some way, like it goes beyond simple interactions with humans. But moreover, like I think some types of data might require some different types of solutions. And one particular aspect is expressivity compute trade-offs. These are like, I'm very interested in those. And I want to understand specifically what is that we understood maybe in the last few years of pre-training language models and several adaptations of those for fine-tuning RL. I'm interested in understanding what are the fundamental aspects of this, and to do that, one of course has to go beyond natural language data, because one wants to discover what are the true, in some way, machine learning principles behind it. And towards that, from deep models and optimization, there's always the question of optimal architecture design, which has a lot of interplay between being optimizable or like being expressive. In some way, like the blend between the two is like how to make architectures which are expressive, efficient, and easy to optimize. So this is in some way my goal. Where we are right now is that we see deep learning, of course, like these are in some way some known, specifically known text kind of breakthroughs of AI. Some, for example, EVO2, genetic code, Nobel Prize of Chemistry a couple of years ago, and some modeling of turbulence about cancer. So there's a lot that goes on beyond text, of course. But however, like if we look at scientists or engineers around the world, and we look at what do they have to do to apply deep learning technologies, this is in some way complicated. The best configurations of architectures are often very unclear. Like you can see here an example of an architecture that was in some way like capable of reasoning in very long sequences. It's like kind of convoluted. There's gates and convolutions, and like there's connections that are a little bit. Yeah, so we don't really know how to connect things yet in deep learning. It's kind of, there's a lot about recently also about linear normalization, where to places. Best paper award in NeurIPS was about gated attention, so if you should use a gate or not. This is the first aspect. We don't really know what people should use. And the second is, it might require a lot of compute to get where you want. And so you might require a dedicated team to develop an architecture and a dedicated team to scale it, and a lot of like compute also in that. So in some way, if we want to truly deliver AI to science and technology, we have to do better. There's also another aspect, which is most of the intuition that we build up in these years has been based on text, has been based on images, and just a few other data domains. Things like, for example, biology, single-cell transcriptomics, which was super important for scientific questions, turbulence, scientific data of any kind about dynamical systems, time series. Those are data domains where way less is ablated, way less has been tried. And in particular, like there is one aspect of this data, for example, EEG or for music or the human genome, is that they usually require long-range dependencies, and the type of data distribution looks very different compared to text. And in some way, we are not really exploring that because we are focusing a lot on text. And of course, in image video domain, we are inheriting a lot of what is known from past pre-LLM areas. So in some way, like we know a lot about text, we know a lot about vision, but in some way we know a lot less about foundations. And for this type of data, where you have a very long sequence length, billions of tokens, there is a clear problem with current methods like attention. I mean, attention is kind of easily trainable, but it doesn't really scale, or it doesn't really make sense when you think about it for this type of data, which is 3 billion tokens. Of course, making interaction matrices between 3 billion tokens, it's something that, yeah, one can see the problem there. There's a memory problem. There's efficiency problems, of course, but also in terms of is it the right model that we want? And of course, this is an open question. For understanding why, I believe that we should move away from models that are quadratic in the sequence length. I always make this example of this Brahms violin sonata. It opens up with 4 themes, the different colors here. And then after these themes are a little bit picked up, there is a variation of the last theme which is presented and closes basically the first piece, the first few lines. And then in some way, the genius of Brahms was to pick up this pattern after 4 million tokens and to present variations. So in some way, like this long-range memory with like extremely long-range dependencies is exactly what made this piece from just a bunch of scales to something which is truly remarkable and worth of being called in some way genius or like a human level intelligence. And this is considered the genius of Brahms, and this is in some way what we are aiming at, systems that could potentially do this. And of course, that would require processing very long sequences. What happened in 2021 is that there was a benchmark called the Long Range Arena, discussing performance of transformers on a bunch of tasks that are very, in some way, long range. Those are artificial tasks. Transformers kind of sucked, especially on this task that was called PathX. But there was a model introduced in 21 by Albert Gu and collaborators that could solve all of these tasks, so very long range, and he had O of L complexity. So that was kind of a breakthrough. It was not really, in some way, kicking off an entire new area of research. But I remember we were super interested in this, because in some way, it seemed that it's kind of killing two birds with one stone. Like it's being more efficient on long sequences, and also it's performing better. And also, by the way, if you do a normal RNN on this is an RNN kind of model. I will discuss what this is. Normal RNNs would not do bad, would not do good at this task, at this benchmark. This is in some way something new. It resembles an RNN. It's very efficient on GPUs, not like a standard RNN, and in some ways going beyond transformers. So super interesting. And of course, after 1 year, LLM people picked up and we were like, oh my God, let's make language models without attention. And so there was a line of research that started from the 3 papers about SSMs. I was fortunate enough to be part of one of them. There was basically like an effort to make this targeted to language models and super efficient, even more efficient than the original models. And you might know models like Mamba, the XLSTM, there's Mamba 2, Mamba 3, there's gated delta-net, gated delta product, log linear attention, and many others. So this sparked an entire new line of research in subquadratic complexity models that have, in some way, maybe an advantage on something, or maybe not. But it's interesting to see from the story here that this was not originally intended from text. Like people were doing this for long range or something. And then in some ways, since this is sequence modeling, kind of adapted this to text. So the story had a moment where people wanted to change things. And the motivation for adapting this was merely an efficiency thing. Like these models were O of L instead of O of L squared. Now, you can make attention not O of L squared, of course. You can use KV caching and a bunch of tricks and checkpointing and whatever, flash attention. But in some way, if the token sequence is super long in the millions, then these tricks are starting to shake a little bit. And also the model class doesn't really seem the right one. So to summarize what we have learned from the past years now, it's been a few years about introducing these models, is that indeed, as I said, at scales like 130,000 tokens, these new RNNs, these SSMs, start to be more efficient in terms of time. And this is kind of the scale about DNA modeling, which is maybe something that goes beyond text, which is why personally I'm very excited about this, because one doesn't need to result in models which have potentially not a very good inductive bias for another task. Like one doesn't need to rely on attention, but can rely maybe on something else. If you train for a long time, people have shown that the performance downstream is equivalent to the one of attention if you train long enough. And also, people have been a bit crazy about this, applying this to the genome, because of course that's kind of the low-hanging fruit. Genome sequences are like 1 million nucleotide length. Of course, you don't want to feed the whole genome, but you can go to context like 1 million. And people have been showing that this hyena DNA, for example, which is a kind of an SSM-inspired architecture, can improve performance and scaling laws. And also, I mean, very recently, like this, just a few months ago, there was a QuEM model that was built up from this. So people are using this also at scale, like at very big scales now. There was an initial drop in interest, like I think in 2024, late 2024, and beginning 25. But this has now picked up again because of this gated delta-net and this new improved SSMs. People are in some way very interested in scaling this up and to provide alternative of the models, which could be kind of more efficient. So I talked a lot about these models, and these models could be great. And potentially, like, by the way, I'm not an RNN fan that has always talked about RNNs in his life and stuff like that. I personally, when I was a student and I was presented first the RNN concept, I thought this was incredibly dumb. Like, because coming from a control system perspective, I know that putting a nonlinearity in a linear system, like simple ReLU or something, could make the system really chaotic. So I thought that doesn't look really a stable way to process tokens or to process a sequence. And I really like the tension. So I don't think I have a particular type of bias towards like RNNs that I was happy to in some way present papers about RNNs working very well. I think there is to understand that these are not the same as old RNNs. These are linear systems. And the conceptual differences are massive. And I'm going to talk about that, and I'm going to talk about some expressivity that these models have, and maybe how they differ from attention, and how they differ from previous RNNs. So it looks like this. You go input, output, attention, you all know how it works. It is scalable, it is trainable. However, inference and memory could be problematic. In new RNNs, they sort of say, I mean, we sort of believe that they have all of these properties. They are scalable, trainable, and also they have good inference and memory. And of course, this depends on the sequence length. I mean, for small sequence length, it could be also that attention is faster than a new RNN. But it depends on the sequence length, and it depends on the implementation. It's also a fun thing to do, to have models that can be different from attention. I think that's theoretically very, very interesting. Like, for the first time, to have something that we can compare attention to. I think that's scientifically needed also to understand attention better. So how does it look like? You see on the top how a previous RNN looked like. From the hidden state Z, well, you take a nonlinearity of a linear function of the previous hidden state and the current input. This doesn't look much different. It looks like the nonlinearity is gone. The matrix A depends on X, but it kind of looks similar, but this A and B depend on X. So that might be a first difference. I must say, interesting, making a matrix and a projection depend on the input itself. But then if we go back to the LSTM, this is exactly what the LSTM was doing, these gating mechanisms. So, okay, yeah, maybe that's not that novel. But notice that the nonlinearity is gone. And this is novel. This is something that people didn't do before. Also, A is diagonal. So this matrix that does the mixing of the hidden state or processes the hidden state is a diagonal matrix. This is for let's say, for the first models in this class, for later things adapted. Also, it can be complex valued, and people have been using complex values here. It is initialized in a very particular way. It is learned in polar coordinates, and it needs to be reparameterized in log space. There's a lot of things going on, and if you're curious, there's this resurrecting paper that I did a couple of years ago that goes through the fact that you actually need all of these steps to make it actually better. Otherwise, you go back to vanishing gradients and stuff. So yeah, this is not really just an RNN. Details really matter here. And there's a plethora of RNNs nowadays that look like this. There's an outdated slide at this point, but there's like hundreds of variants of this. But sort of like at test time, they can all be written as something like this. So the dependency between Z and K-1 is a linear function of the input. And that's mainly in some way if you want to think about a test time, not a training time, that's the main difference. So there is a linearity thing, and that's crucial, plus the parameterization, which also implies stability. So 2024, we were curious about the fact of like analyzing this a little bit differently and seeing like what does really unlock performance in these models. And it's actually diagonality. So the fact that a matrix is diagonal actually implies that the optimization properties of Adam kind of blend in very well with the structure of the model. And so this actually makes the networks trainable. Also, it's interesting to see this is applied in a different way from the original deep RNNs. Like if you look at 2014, this is also interesting. RNNs are models from the past in a sense. Like people consider this as like building up a memory of the system and kind of a Turing machine. So they're shallow system. There's one RNN that processes an input, but the features might be computed in a deep way. So that's what people thought about in 2014. It was like this how to construct deep RNNs by Benjo in 2014. It was thought as, well, let's construct deep features and put an RNN on top, and then like do something else on top. But this is not at all what we consider them as today. Like this is a crucial difference. We're not thinking about RNNs in the same way as 2014. We're considering them as blocks. So we have blocks as if we have attention blocks and we stack them together. So this is also crucial, thinking about RNNs as token mixers and not as Turing machines. So this has been a kind of a paradigm shift, but also can be seen in models like the LSTM by Google in 2017. Okay, so it all seems I'm saying like, oh, this is great. It's actually new. There's a lot of positive aspects. What's the catch? So why is that probably you guys are still using softmax attention? So Exhibit A present like a few things that are actually not good. I told you that the performance is comparable to softmax attention if you train long enough. But indeed, if you don't, like if you have, for example, 1.1 trillion token instead of 3.5, then you can see MMLU performance. So that requires strong copying in context learning abilities. This is actually not very good. Like, so in context learning is unlocked, but you need to train for longer. And who knows basically what is exactly the comparison here, right? It seems that to pick up some particular aspects of language modeling, the model takes a long time. However, from this NVIDIA study, this is an NVIDIA study, you also see here figure 5 that there is an inference speed up which can be also 7 times faster at a context of 100,000 tokens. And just to remind you, these people are like, there's 3 DAO in the paper. So there's people that really implemented flash attention in the right way. This is not say a brutal implementation of softmax attention. This is a very carefully done one. And you still see an improvement in inference, but you also see like that, you see what I said, like capabilities might be impaired if you don't train long enough. And this is MLU. Of course, you all know what MLU is. It's just like a reminder for you that are interested, maybe. Exhibit B, needle in a haystack. This is perhaps the biggest reason why these models are not used, let's say, by industry on a daily basis, is because needle in a haystack, which is a task that requires. So needle in a haystack is the following: you have a large collection of books. You put in a sentence in the middle of a book which has nothing to do with the book, and you ask the model to retrieve. To ask the model a question regarding the little piece that you inserted in a book. Of course, the task doesn't make any sense from a point of view of memorization, right? Or compression, or learning, perhaps. So what this tests is the model capabilities of at test time having full access to the context. So if you read a book and then in the middle there is a splash of coffee or something like an interesting pattern, maybe you will not pay attention to exactly that pattern and you will continue with the book. And that's indeed what the RNNs are doing here. Attention, though, by the way of its construction, has access to all previous history and therefore could do this task. And here you see that indeed these models like Mamba2, log linear attention, they are not really at transformer level for needle in a haystack. And needle in a haystack is very important for search then, for search engine capabilities. So yeah, that's pretty important. And these models cannot do it very well. They can do it to some extent, but in some way, the way they look at the context is very different from a transformer, which might be good in some situations, might be bad in others. This is a case where it's actually bad. Exhibit C is about Chomsky hierarchy, it's called like that. I mean, it's basically you have a bunch of tasks which are provably one is like different from the other in terms of like grammar. So it requires different type of capabilities of language models to do these tasks. And you can see that, well, Mamba, for example, if you see the second line and attention, yeah, they both suck at a bunch of tasks like modular arithmetics and things like that. But for example, they cannot be as good as an LSTM in modular arithmetics. This is, of course, the XLSTM paper, so they wanted to show that they could actually do it better, but XLSTM is not as efficient. So these two first lines, let's say Mamba and Llama, they have similar performance on these tasks, but they cannot do parity. They cannot do modular arithmetics with brackets or without brackets or solving equations. So these things is sort of like not bad just for Mamba or SSMs, but it tells, yeah, I mean, there are things that both attention and SSM still cannot do. And this is, of course, a big motivation for our work. Exhibit E, is that the letters? Oh, this is a D, not E. So in some way, like these models are also used for genomics. And people have been showing that these models are super efficient and can process a lot of tokens, and scaling laws are better. And we're able to replicate that. So indeed, if you take a hyena model or a mamba model, they have a perplexity, test perplexity, which is lower than transformers. So it seems like it can model the genome better in terms of next token prediction. However, what we found is that, and this is basically the point of the paper, is that it is not true at all, but this implies better downstream performance. So indeed, we see that the performance is kind of similar. Like there's maybe a 2% difference, but this is not enough in a sense to motivate that these models are exponentially better, as it was stated, for example, in the hyena paper. And the problem there is that they didn't really have a fair comparison in terms of model sizes and in terms of data budget. So we do that and we see, yeah, I mean, it seems better, but not maybe as good as was thought. And this is like some other papers that also point out to the fact that the genomic foundation models also kind of don't profit from pre-training at all. So in some way also that makes us rethink a little bit, is the pipeline really of pre-training and next token prediction, evaluating performance there, is it really something needed or should we look for something else? This is a bit of an aside, but I thought it's good to put in consideration the fact that the pre-training fine-tuning paradigm, it falls apart if you are not reading text, like can fall apart, or it might not be worth it, simply not worth it. Maybe it gives you 1% better, but it's not worth it. So it's good to consider that when talking about all of these things. Well, it's clear that we need to improve capabilities, right? I mean, it's clear that, I mean, given also the fact that these models, if pre-trained, they don't really profit much for pre-training. Anyways, they have problems in simple tasks. So recall and copy capabilities in these efficient models is a bit impaired. I mean, it's clear that we need to do better, or we need to understand things better first. So this relates also, like, I like to think about this problem, this fundamental trade-off between like computation and expressivity. It was already outlined in the Ellman paper, 1990. This is actually an extremely nice paper, finding structure in time, basically saying, say we have to do a network that processes a sequence. How do we do this? There are two ways. The first way is to basically, make it a vector, like make a sequence the vector and just go on with that. This is basically what attention is doing in some sense, because it, in some way, that's exactly the reason why it's quadratic, is because it's considering the sequence not really as a sequence, but as a set. And indeed, the attention doesn't have a position embedded into that. You need to add positional embeddings. Another way, it's written by the paper, very different possibility, is to allow time to represented by the effect it has on processing. And this is indeed a very different paradigm. Okay, so these are the crucial difference between RNNs and attention can be phrased as follows. So this is just to remind ourselves of the problem. SSMs, if you want to be, a bit more precise, cannot copy well, cannot do association well, if I can do it worse than attention, and they cannot track state well, but also tracking state, which is a fundamental capability, for example, for solving chess or other problems, Sudoku. This is something that also transformers struggle with. So we, of course, like the group is mostly about theory. Like, I mean, we have a few papers about expressivity of these models. along with precise guarantees for recall in RNNs. But what I want to present you is maybe kind of the most important aspect of this. Let's go back to vanilla RNNs. Why did people like it? Like, people liked RNNs in the 90s, in the early 2000s, LSTMs and stuff like that, is because they are indeed Turing machines. And AI, Turing machines, I mean, they go very well together. And indeed, this is a dynamical system. One can see a vanilla RNN as a dynamical system, which can approximate any nonlinear dynamical system that you might want. And there's a few papers about it, about the connection between an RNN and approximation of nonlinear dynamical systems, and also about the approximation with of basically Turing machines. Very early results. Transformers don't have such strong results in a way, but these models are also not very efficient. So what do we show in a publication that was NeurIPS 2024? It was not the latest NeurIPS, it was the one before. What we showed is that actually the structure of A, the fact that it is diagonal, kind of hurts expressivity. What you really would want is a dense RNN. And to do that, I mean, if you stack layers, that's fine. But if you really want to have expressivity of a block like really boosted, you would need A to be non-diagonal. And unfortunately, that's very bad news for efficiency, because A diagonal means efficient. A non-diagonal, less efficient. So to do this, to prove this result, which is in some way like the equivalent of a general approximation theorem for this system, which are, again, not nonlinear RNNs and not linear RNNs. They're something in between. They're linear time variant RNNs. We use rough path theory and the concept of signature. So just to give you a little bit, maybe you're interested into this. What we prove is that one-layer dense Mamba layers without MLPs can approximate any nonlinear dynamical systems. The way we do this is through basically a Taylor expansion. You can show that if you have a system, for example, with two variables here evolving over time, if you take the signature, that's basically like a featureization of the time series. So you go from time to features. So you can build up a sequence of features more and more representative of particular aspects of the signal. And if you go on forever, you will capture all the signal. And then there is Lyon's theorem. And Terry Lyons is in the paper, so we were super glad for his help in the early 2000s, that showed that basically any continuous function from a path, from a sequence to a real number, can be expressed as a linear map on the signature. That's super cool, because it tells us, well, there is in some way a sequence of features that one can have of a signal which kind of completely describe it by means of all possible continuous functions from L2, like some class of functions, to real numbers. We call this path to point. And for example, a similar way to think about it is like, if your features are just time, then the signature of time is the Taylor terms of time. And then if you consider, you can write any function at time t as a linear combination of some numbers, which are exactly the derivatives, times basically the features. So basically, Taylor theorem is a very specific case of what I just said. Turns out that you can do this for every type of system, for any type of input, not just a simple time processing. And so like what we show is actually that Mamba is a random projection of the signature. And then random projection through Johnson-Lindner-Strauss lemma, they have density results, meaning that they are enough. And so through that, we're able to show that Mamba can actually be super expressive. The problem is that you need to be dense. And here you have, like, this is state tracking from the illusion of state, another paper that points out something about density. So what we have is that Mamba layers and attention layers, here's the number of layers needed for solving a task. In this case is A5. And what we have is indeed that you need a lot of layers for Mamba transformers. But if you have a dense Mamba layer, that's the brown curve here, you need just one layer. So this is just a proof of concept. It's not about efficient implementation or anything. But it's kind of telling us that the theory is right. Like, the way to make this network expressive is to actually make them more dense. The problem is efficiency. So, and also another aspect of this is that we don't really know how dense we need, or do we need actually to be dense? We don't want to build a very dense architecture and then in the end we don't need it. It might depend on the task. So maybe the idea is, how about being adaptively dense? Maybe you require to be just a little bit more dense, or maybe like at test time, you decide if you want to be dense or not. It's kind of a crazy idea. So we did this for NeurIPS last year. It was a spotlight on NeurIPS. It's called fixed point RNNs, interpolating from diagonal to dense. What we show is that we can build the first model, which is recurrent, which is state-of-the-art at the same time in both state tracking and copying. And notice that if you notice the plot on the left, LSTMs are very good at state tracking, like A5, but they suck at copying. And attention would have a similar kind of comparison and issues. What we have is a model that can do both at the same time. And about state tracking, you can see the plot on the right about indeed the test time adaptation. So you have LSTMs, which are extremely good at state tracking. Here, the purple one. And here is length generalization. Of course, you want to do sequences and track states and just solve problems, kind of mathematical problems, at a length which is not the training length. You want it to be more difficult. And this is like, again, the pink line. Transformers are really, really terrible at doing this if you don't have enough layers. LSTMs can do this no problem. What we show is that by test time adaptation, we can interpolate between these two performances and sort of build a very flexible architecture, which if we put in more budget of compute, can give us the result. How does it work? So here's a bit of math about this trick, about making a network more and more dense. So let's start from a general case. Consider Q to be an orthogonal matrix and lambda to be a diagonal matrix. The product of this is a dense matrix. And here I write it as a first formula. Okay, this would be the thing that we want to compute, a dense RNN, linear, time dependent. Notice indeed that this Q depends on time. So this might depend on the input. Now multiply everything by Q. You put Q minus 1, but it doesn't matter. Like it could be Q or Q minus 1, doesn't matter because it's an orthogonal matrix. Multiply everything by Q. The Q here disappears. And then add HT to both sides. And then what you get is the following RNN, which is interesting. I mean, there's a clear catch here. You have HT here, and you have HT. So this is an implicit formula. It's not giving you an update step. It is implicit. However, note that the dependency on the previous hidden state is a diagonal matrix. So this will be efficient. So the idea is, how about we compute this recurrence recursively? So we have a second recurrence that computes the fixed point, computes this implicit equation, and this is the upper superscript, and the subscript is time. So we have two time now. One is depth, and one is actually time. And this trick, so we have a bunch of theorems in the paper that show that actually this is able to go to the right solution. The architecture looks something like this. We explore like what are the efficiency, expressivity trade-offs of this compared to doing L layers of just like, because this looks like an RNN repeated L times. You have way less parameters. You know very well the limiting object, and training is more efficient because indeed the fact that this converges to a fixed point implies that you can compute gradients at the fixed point. So you don't have to backpropagate through the recursion of the recursion. So training these models is as efficient as training a Mamba model. However, at test time and the forward pass, we're doing something else. So what we have is like this Q matrix that was basically orthogonal, could be something else. And so we explore it could be diagonal plus low rank, Householder, Kronecker, and we show that throughout, like some particular choices allow us to do more in particular settings. One other aspect is, for example, I mean, I told you that attention and Mamba, they are terrible at modular arithmetics, which is kind of a reasoning task, which, I mean, we want to be able to solve also for downstream, right? In language models, we will want models to pick up this type of tasks very easily. What we show is that with the fixed point Mamba, which is this architecture that I'm presenting now, you're able to reach performance which is close to a gated delta product, which is one of the most, let's say, blue sky type of RNNs, which is actually dense. And that does this in an efficient way. We do it in a different way. We are slightly better. And also, kind of interestingly, the model adapts the compute time really depending on the data point. And so this is quite cute to see. Since language modeling, right? I mean, does it actually, can you minimize perplexity with it? Yeah, you can minimize perplexity. It actually works a little bit better than Mamba. But this is, of course, not a thorough ablation. It is just to say, well, you can do language models with this. It's possible. It's not terribly inefficient. Of course, the forward pass, by the nature of it, will require to try different type of depth levels, but this is not the whole story. Okay, I wanted to tell you one other thing, one last thing. So in some way, this is one paradigm, adaptive compute. But what if we want to add, to rethink the block a little bit? Well, we know that density is one aspect. One other aspect is, some things about softmax attention we really like. Do we really understand how these models compare in terms of token mixing? Well, we have this iClear paper, the latest for this spring, that explores a different type of RNN, which is inspired by softmax attention. Now I'm going to do a calculation. I hope you enjoy this. A simple calculation of how you can make attention around an RNN through random features. And from that, we get insights into building a new model. So let's start from the definition of softmax attention. What you should pay attention to is just the fact that, of course, like the attention scores are basically the exponential of a query times key, right? And the fact is that softmax attention is not separable. So you cannot really separate queries and keys and compute this product in a like exponential of query times exponential of keys. This is the whole reason why softmax is O of L squared. However, define the following features and note that this is a complex number, complex unit. So for a vector W, we define these random features, which are basically the norm of X, times some potentially random rotation of X defined by this vector W. What we show is that the attention scores can be written as the real part of the expectation with respect to omegas sampled in a normal distribution of separable featureized queries and keys. So the big difference here is that the nonlinearity here wraps the product, and instead here, the nonlinearity is applied element-wise. This is the fundamental difference between attention and RNNs. The catch here is that, of course, this is an expectation. So you will need, in some way, infinite features. So you will need the W's to go to infinity, to have actually the law of large numbers kicking in. Like, I mean, you need to be very big, but you can think about an approximation. So we can rewrite this as simply like just taking the exponentials out. And this is basically rewriting the formula that I showed you. You can, of course, approximate it with a finite sum. And here you go, like you have a second line. Let's now consider a single W. Sorry, I call it W, but it should be omega. Omega. A single omega j. So you delete this sum, right? This is what you have. You just have a sum over data points of this exponential. Some of them are real, some of them are complex. And now comes the trick. So what you can show through a calculation is that if queries and keys have equal norm and equal to 1, then you can write this computation as an RNN. But crucially, and this is the crucial thing that in some way we notice, the A matrix, so the rotation, the hidden state to hidden state transition, depends on the query and is complex valued. So this is a rotation. This is not a diagonal RNN. This is a dense RNN where actually the say hidden state to hidden state transition is controlled by the query and is a rotation. And so we were like, oh damn, but this looks very different from what we're doing right now. So let's actually try to build an RNN which is in some way closer to softmax attention. So what we do is you can write this down, of course, in matrix form as follows. And what we have is that you could think about R, this matrix R, here as on the right-hand side because of the matrix notation. You can just put this to be a diagonal matrix where the entries are actually complex valued but depend on the query. And the real trick here is the complex values. So this rotation is not really a full rotation, but it's just in some way what complex number would give. So 2 by 2 blocks. If we do this, then suddenly, and if we apply this to standard things like gated linear attention, which is one RNN, which is very flexible, then you can see here we have the comparison with so no positional encoding, no trick about the rotation. We call it rotary positional encoding selective. So you can compare this with the simple putting in positional encodings, or just simply not having any positional encoding, or to put in our trick written in terms of positional encoding. If you do this, which is, by the way, very efficient, you have improved performance in both copying and associative recall. And here we have the red line here and the purple one here. So this doesn't really just do copying better, but also does state tracking much, much better. It turns out that you can track states. And this is kind of unreasonable. But this is like because transformers are not really made for this. However, transformers with rotary positional embeddings are kind of better than RNNs on this task. So what you can show here is that this connection between softmax and density actually makes it blend very well together. So in some way, it's a bit unreasonable that you perform very well in state tracking because transformers are not very good. But if you add this trick also to transformers, since in some way it implies some sort of density of a correspondent RNN, then you actually improve performance. So through all the models, you can put this as a positional embedding because this can be written in some way in a rope fashion, but you can apply this everywhere. And also, these are silly numbers. I don't like these comparisons, but you can show also that downstream this is better. And with this, I thank you. And if you have any question, I'm here for you. And thanks a lot for your attention.
Thank you so much, Antonio.
Thank you.
Nice talk. Thank you. So yeah, let's open for questions. Are there any questions from the audience? Yes, Fabio, go ahead.
Okay. Hello, everyone. Can you hear me? Yes.
Hey.
Okay. Thank you for the very nice, presentation on those models. And I have two questions basically. Maybe I can start from the more technical one. I was very impressed by the idea of using an implicit solution to get the next state. So
Yes.
in the part where you move from diagonal to dense metrics. And in particular, I wanted to ask about the orthogonal matrix Q. I noticed that I understood that you parameterized it by householder or maybe some other, let's say, low rank structure. I don't remember exactly how.
Mm-hmm.
But my question is, did you do that for efficiency reason, or there was also some, I don't know, convergence or stability result?
This is a very good question. You indeed cannot choose whatever you want. I mean, for sure, you want this to be invertible. But also, in some way, you don't need to be. So in some way, this is a motivation. But then you can just apply this to anything, right? I mean, you can just apply this formula to anything, and then you kind of hope that if there is no inverse, maybe there is a pseudo inverse. Like inverses here are kind of a bottleneck. You don't really need this because the concept of inversion is also a very abstract one, and so there's that aspect. So, but going back to your question, yes, you do this for efficiency because these operations here, they can be pretty expensive, like this projections. So it's not so this operations turn out to be kind of expensive. So that's why we have in some way not the most general matrix. And there is also a second aspect. the aspect is you have a matrix which is dependent on an input. How do you make a matrix dependent on an input? It's quite strange, right? I mean, an householder transition, maybe we have the formulas here of the householder and stuff. Yeah, I mean, this diagonal, let's take, for example, the householder refractions. This is the product of identity minus a scalar times U transpose, where U is a vector. Well, in that case, you can make the U's dependent on the input. And that's a matrix transformation, right? But if you want to make a matrix dependent on an input, kind of the projection that you need is massive, right? So this is also in terms of parameter efficiency. And as I said before, in terms like you cannot really compute this efficiently if you have a general transformation. What you need is to restrict the input dependency. And these are tricks to do that, basically. I hope this replies to your question.
Yeah, I think, yeah, very clear. Although, because you don't want a method that relies on multiple iterations, for example, to deduce a matrix Q from input, otherwise would be hyper expensive.
Exactly.
Amazing. Okay. Yeah, the last question is more, let's say, more or less technical. In slide 31, you said that the model can be presented as a model without nonlinearity.
Yes.
Yeah, but probably the nonlinearity, is it embedded in the computation of the matrix A? Is this the case?
Yeah,
and I mean, also, are you aware of any study that tried to provide guarantees on stability, for example, looking at the eigenvalues of A or something similar to Lyapunov stability, let's say?
I mean, stability for this system is kind of trivial because you parameterize this in polar coordinates. So like you can guarantee de facto that your eigenvalues are less than 1 just by simple parameterization. So this is one very crucial difference also to previous RNNs where your A is free to evolve and you can get unstable. Here, parameterization, I mean, without being obscure into this, like you parameterize this as the exponential of minus something. So that's always less than 1, right? So that's the trick. So stability is studied, and there's a lot that is said about it, but also like it's simple. Expressivity, I mean, we have this. So there are many aspects of this. Like what we have is this was like. So this paper, I mean, it's not the easiest read, but this is in some way providing the NTK. So this is actually characterizing precisely what this model class does. Because you're right that the nonlinearity comes into A, but this is actually a completely different class of system. Like nonlinear dynamics is not linear time variant dynamics. These are completely different, right? I mean, this is completely two different class of systems. And therefore they have different properties. It turns out that one can approximate the other, but you need A to be dense. So that's indeed what we prove here.
Okay, thank you a lot.
Thank you.
Okay, Maura, yeah, go ahead.
Hey, thank you for a really interesting talk. I will need to decode the last part because it's a bit more technical, but I got the main idea, and I'm not very familiar actually with even with Mamba models. So I'm really curious about the security aspects because to connect it to our world. You said something, first of all, about the needle in the haystack.
Yeah.
Is it studied also in the context of memorization? Because, I mean, it's not really too much of a problem if you see it from the other side. If you say, if the model doesn't spit out information that was memorized from some copyrighted text or code that is not supposed to be memorized. So I'm curious if you're aware of any paper that studied this.
That's a question. That's a very good question. I think there is not a dedicated paper that studies a needle in a haystack with different models, and especially what this means. I think it would be a super cool paper to see.
I mean, I'm curious if it's some sort of less overfitting that is supposed to be good.
Yeah, I mean, I think this is a test time. So this doesn't require any training. This is just a zero shot, right? Because indeed that's what you want. Like this came from a blog. I don't know if you are familiar with this GitHub repository, but this is a GitHub repository. And basically, this guy like made a crazy YouTube video about. I was curious about this in language models, just like putting a lot of junk around the information and try to see if the model can figure out the junk. But then the guy was basically like just prompting language. It was literally copying this to ChatGPT and seeing if if he could do it. Like yeah, I think like the problem maybe is also that we don't have models at the scale that is like where we could see these things happening, or maybe it will come with more training. But yes, indeed, this is the thing is okay. So being a bit more careful with your question. One fundamental difference is that people believe that if you are an RNN, you have to make trade-offs because you have a finite hidden state, and that implies that your memory and you don't see the input again. So whatever is in your hidden state, you need to organize better and you need to make precise because indeed you cannot go back in the past. So and you don't know the query beforehand, right? If you were to know the query beforehand, it would be different. But if I give you the text and then I give you the question, then in some way the hidden state, I mean, it's indeed not overfitting, right? So it's not memorizing everything. It's kind of making sense of the paragraph and will probably filter it out. So yeah, this is what people think. It's a little bit because it's not exactly, but yeah, it's what I mean. It's kind of debated still, but it's an interesting question.
Okay, and another question about security, because as you talked about the long context length, actually extreme context length. Let's go to extreme. How about sequences that introduce some failure mode that you see a long time later?
Can you make an example?
I don't know the exact application of these models, if it involves also some security related aspects, like, I don't know, scanning some sequence of actions that are monitored, and if you can somehow induce a hidden state that is just collapsing, and then the rest that the model sees goes nowhere.
So you're worried about the hidden state containing or not containing information? Wait, I didn't get.
The hidden state ending up in something that is not recoverable. So it just stops kind of understanding the rest because the sequence is long and there are hidden, I don't know, parts of the sequence that on their own they don't cause the problem, but if you take them in a long context and they are difficult to spot. But this is like probably something to worry about in the future.
No, I mean, you're right. Also, this in some way it relates to the fact that, for example, the input dependency of A and B could be dangerous because you can make an attack that simply modifies an input that erases the memory. You can do it like 100%.
Yeah, this kind of.
Yeah,
I was exactly thinking of something like that.
Yeah, you can.
Which you can degrade the model for future use at test time, I guess, like during the use. Okay, I see.
Yeah, it's an interesting point. I had never thought about it. Like, I think it's interesting.
Well, if you're if you want to exchange some ideas, of course.
Yeah, for sure. I would be happy to.
All right. I have to read some papers before.
Me as well.
Okay, nice. So yeah, let's see if there are any other questions, or otherwise we can close. Okay. Yeah, nice. Yeah, please go ahead. We can't hear you, or maybe.
How about now?
Yes.
Okay, perfect. Thank you for the very interesting talk. I think, like Maura, I didn't follow so much the technical part at the very end, but I got the general ideas. What I don't understand so well is the intuition behind the behavior of what these dense member or fixed point RNN type models you describe are doing. Fine. Transformers, you have the whole token string, you can attend to any point, you mix them through the layers, and okay, you can do intelligence that way. RNN, okay, you have a state, and you store everything in the state, so they're good tasks that involve, I guess, compression, or anything that can be efficiently packed into the state. Yes. In dense member, and in this fixed point, adaptively dense kind of member, what is the model doing? Is it deciding to be able to attend to parts of the input depending on the state? Or what is the actual decision it's making to be adaptive? I get the maths, but I don't get what's happening.
Yeah, I mean, this is like a little bit where the connections are actually like. Yeah, I mean, the problem is that it's actually this connection. So I sort of disagree, but this is like kind of, my opinion, that the RNNs really have a hidden state in a sense. Like it's a little bit different. Like, for example, there is this paper that is, where was it? It's called the illusion of state in state-space models.
Okay.
There is no state. I mean, it's actually true that they don't really have a state. So in some way, like the intuition, like you see the hidden state being there and being a variable, but actually the hidden state would actually not be generated. What this is actually is mixing tokens, similarly to softmax, but in a different way. Like it's basically, so this is also what in some way you can see here. Like, so in this derivation that I presented quickly, you can show that attention can also be seen with having a state. Like attention can also be seen in a stateful way. And so the comparison is a little bit brittle there. What is true is that Mamba compares features in a more systematic way. And instead, what Mamba does is a much more simple way of construction of the attention matrix. It's all about how you construct the attention matrix. It's not really about that you have or not have an hidden state.
Okay, but what it means for Mamba to be diagonal is precisely that it's only attending to the previous iteration at each step, right? Or am I misunderstanding what you mean by diagonality?
It means that it's mixing features. It means that it's mixing features, basically. So like the way that you see the past is like the way that you see the past, the hidden state, in some way, the way that you see, the features are mixed in a more complex way. Basically, like you can see this as the entries of the attention matrix. The attention matrix, the corresponding attention matrix of Mamba 1 diagonal is not a diagonal attention matrix. Like you have dependency on the past. If you are dense, these dependencies are much more sophisticated. So it basically is about they both have attention they both have an attention matrix. This is Mamba 2 paper. If you read Mamba 2 paper, that is like making the connection between attention and Mamba. They both can be seen as multiplication with a lower triangular matrix. However, the way that you construct the coefficients, it's different. That's the main point. That's just about that. At least in my opinion.
Okay, so we should not think of these SM models as doing what an RNN does and just as a different way of calculating.
Exactly. Exactly. This is indeed the point here is that indeed the attention, softmax attention does query keys and then makes an exponential and then normalizes. Okay. But like an RNN cannot do this, cannot do this type of nonlinearity and division. To construct the attention matrix is bound to basically working on separable type of feature of attention. So something like this, nonlinearity with wrap queries and keys individually. And this is the main difference in a sense. Like the difference is all here. The difference is having a nonlinearity on a 2 by on an L by L matrix versus having nonlinearities that wrap elements. This is the only difference.
Okay, I will read the state papers and hopefully it'll make more sense to me. Thank you.
Okay, no, it's not an easy point, but it's an important one. Yeah.
Thanks.
Okay, thank you so much. Thank you, Antonio, for giving the talk. It was super interesting, and with this, we can close today's episode. And yeah, thank you everyone for participating.
Thanks so much. Thanks so much for the invitation. And goodbye. Have a
Thank you,
nice
Antonio.
evening. Ciao, ciao.